Okay, so the last time we talked about a numerical method called Euler's method introduced by Euler in the 18th century, long time ago. And through this numerical approximation, we could predict where would the solution be at a certain time. And what we did was we discretized the time into small segments and then iteratively find out what would be the solution at each time step, given that we know the slope field at the previous time step. And okay, then there was a question about the accuracy of the solution. So at the end of the day, what we need is an accurate answer. And when we are using a numerical method to solve a differential equation, we will not get the exact solution. So there we have to let some error to happen. So we call it as what is the order of accuracy we want, or what is the level of accuracy we want to solve this numerically. Okay, let's say we have set that thing up, and then to achieve that level of accuracy, there are a couple of factors that are affecting it. One is the time step. Okay, we observe that when the time step is smaller, it produces a quite accurate, or it reaches the accuracy level quite quickly. That means we also learn about that the order of accuracy of this Euler's method is first order, saying that if you want to improve the accuracy by 2 times, I have to reduce the time step by half. It's directly proportional to the time step. That means if you want to achieve a high level of accuracy, we need to have a very fine time step. That means lot of computations. But computations comes with a cost. So people thought about it and thought about whether we can come up with some improvements to this method so that we can reach the same level of accuracy but with fewer computations. Okay, Hume introduced a method to improve this Euler's method, which we sometimes called as the Hume's method or the improved Euler's method. And using this method, he could improve the accuracy with comparatively higher time step. That means per 1 time step, the calculations are slightly more than for the Euler's method, but if we decrease the time step by half in this method, we will see that the accuracy increases by 2 times. Okay, so the order of accuracy would be h squared. So the accuracy is improving in the quadratic way if we are halving the time step. Okay, so that's good. And then can there be even superior methods that have even higher order of accuracy? Yeah, if there are, then that's amazing, right? That's what we want, because what we want is to get an accurate answer to the level of accuracy we want in fewer calculations. And the RK methods, it's not just one method, it's a series of methods which are known as the Runge-Kutta methods, are having even higher order of accuracy. Okay, so we're going to learn about them. So particularly we're going to learn just one method out of all them. So that's third order method, the fourth order, fifth order, sixth order, I don't know, 40th order, 45th order. Yeah, so different order of accuracy methods can be developed, but we're going to particularly looking at a fourth order one. That means if I half the time step, the accuracy will be 4 times, which is much better. Okay, so it is again an improvement of the Euler's method. There we looking at 4 different slope fields at different time instances and make some superposition of them to get the final answer. Okay, so now the question that one might think is, okay, I have this problem, I have developed a mathematical model to study this physical system, and I figured out that I need to use a numerical method. Which one to be used? Okay, so it's a good question, right? And what sort of accuracy I want, and let's say we know that. So then there's a question which method to be choose and what time step value to be choose. So let's discuss about those things as well in the lecture. And if someone is really going to use a numerical method to solve a differential equations, they use a much higher order differential an approximation method. For example, the last week in the workshop 3, we use ODE45, an inbuilt ODE solver, which has much more accurate prediction. Okay, so it's also a numerical approximation. Okay, so that's what we're going to discuss in this lecture. See you in the lecture. Bye bye.